Hi, everyone. I am really excited to share with you all some of my recent thinking around socio-technical congruence within AI software development teams and our vision for human-centered AI. Before I get started, I'd like to acknowledge my wonderful collaborators and the projects I will be presenting today. So, over the last 20 years, we've gotten really good at incorporating human-centered design into software engineering workflows. We have created new roles and expertise and developed tools and processes to really drive software design based on human needs. User experience designers, who are experts at understanding human behavior, usability, and design, work with end users to identify their goals and challenges. They then create software design solutions and hand off these specifications to engineers who are trained in software programming and can build systems based on these requirements. To make it a bit more concrete, imagine designing a user experience to unlock the phone by taking a human-centered approach. If you are a designer, you would first try to understand when, where, and how people use their phones and what their security concerns are. You'll then translate this understanding into a set of design needs, such as quick to unlock and low cognitive effort to remember. Next, you will prototype various solution alternatives, such as a numeric key code, alphanumeric password, or pattern-based unlock, and you will gather feedback from end users and say, determine that a numeric keypad is the best option. We have a number of UI prototyping tools that allow designers to create interactive click-through prototypes without writing a single line of code. And at this point, as a designer, you have fully defined the software design for the phone unlock experience, including the interface design, interactions, and behavior level details. You'll then hand off these specifications to the engineer to build. And the interaction between designers and engineers is largely that of coordination and handoff. Now imagine designing an AI-based phone unlock user experience, one that uses facial identification technology to authenticate users. The user interface itself is quite simple and consists of a blank screen and a single lock icon. And this interface experience should support diverse users and various contexts of use. Unfortunately, unlike conventional software, designers cannot fully specify the human-centered AI experience at the user interface level alone. Design extends beyond the interface and into the design of different AI subcomponents, including model design, model implementation, as well as in specifying the training data needs. And because building AI software requires writing meta programs to learn from data and examples, engineers cannot build systems to exact specifications. Which means, unlike before, a coordination and handoff approach between designers and engineers is no longer viable. In fact, prior literature has highlighted numerous challenges in bringing human-centered design into software workflows. Designers find it challenging to understand machine learning capabilities and represent ML dependencies on data. They find it difficult to prototype AI features and to bring this human-centered view into the AI component design. And for engineers, current workflows don't do a good job at designing data needs. Engineers tend to focus more on machine learning models and view data as non-technical. And lastly, the UX and AI professionals have different priorities and incentives, and we lack tools and processes to align AI advancements and user experience design. So in the last couple of years, I've been looking at how to support UX designers and AI engineers to collaboratively design human-centered AI experiences from the ground up. Companies like Microsoft, Google, and Apple are putting out these design guidelines and best practices for human-centered AI. And I started off with the project with this goal to understand how industry practitioners are currently operationalizing these guidelines in practice. I collected around 280 design guidelines from various industry sources, and I conducted an affinity diagramming exercise to identify the key components and tasks in designing AI experiences. I found that the guidelines cover both UX and AI design. That is, they recommend that we center people in the design of the user interface and interaction, as well as in the design of AI behavior, implementation, and training data. For instance, for training data, these guidelines, make recommendations for how to align like human needs with AI's data needs, ways to collect the data, ways to label the data, as well as in thinking about users' privacy and security. For instance, one of the guidelines says we should consider what information would a human need if they had to perform the task, and then base AI's data needs, based on human needs. Similarly, in designing the AI model and implementation, we need to align the design performance and how we evaluate performance, as well as learnability based on humans. That is, when designing automation, we should consider if a human were to perform a task, what assumptions would they make? Similarly, at the user interface level, these guidelines recommend that we align the interface inputs and outputs, explainability, failures, and feedback based on human needs. That is, one of the guidelines says, assess automation versus augmentation. An imperfect algorithm can be used not to automate decisions, but rather to generate anchor points to augment and improve human decisions. So in designing this human-centered AI, we need to make sure that we align the AIX design or the AI experience design with the human's mental models about their tasks, their expectations about what they want the AI to do for them and what they do not want the AI to do for them, as well as how they want to interact with different AI capabilities, that is their interaction model. So using this model as a guide from the guidelines, I conducted a set of semi-structured interviews, that is 21 interviews from people across 14 different organizations. My participants included 7 AI software engineers, 6 user experience designers, 3 product managers, 3 data scientists, and 2 AI research scientists. I recruited them through my network initially, and then through snowball sampling by asking them to refer me to other people within their teams. And each interview lasted about 60 minutes. And I used qualitative in vivo coding to analyze the transcripts. And then I also wrote a set of memos and had discussions with my collaborators on the findings. Briefly, to give you a sense of the work team structure, many large organizations consist of these core AI research and UX teams that worked on developing new AI capabilities. And some organizations also had in-house domain experts and legal consultants. In addition, in larger organizations, they had these dedicated bridge teams who are who create prototypes and demos of, envisioning demos of AI prototypes in order to, do technology transfer to product teams. And of course, larger companies have several different product teams, but smaller companies, were limited to a single product team. And each product team may consist of a manager, backend developers, front-end developers, and product user experience designers. And lastly, many of these companies work with external entities, for smaller companies who don't have in-house core AI development team, they make use of third-party AI. But also all of these teams work with data annotators, university interns, and test users. So this gives you an overview of the team structure across these organizations that we interviewed from. And I'll now talk about 2 key findings from the study. The first finding is that design engineering boundaries pose specific challenges to the cross-disciplinary needs of AI experience design. In conventional software, the user interface acts as a natural seam for designers and engineers to coordinate. And given their differing expertise, the practice of information hiding and abstraction allows them to work effectively. That is, designers don't share low-level details such as notes from user observation or prototype alternatives with engineers. As one of our participants commented, they, that is engineers, are blindsided to sketches, wireframes, and any other low-fidelity prototyping. They only understand high-fidelity prototyping, even more so if it is interactive. Similarly, engineers don't need to share technical details about how they will implement this design. But this approach becomes problematic for AI experience design. Specifically, these design engineering boundaries introduce knowledge blindness between designers and engineers. That is, designers don't get to understand essential details about the AI that is necessary for AIX design. And engineers don't get to understand details about people. So as one of our designer commented, you have these requirements. So they were doing this, they were building this AI-powered video analysis system, and they commented about the challenges in designing this in a human-centered way. you have these requirements where you need to tag these videos to be analyzed and categorized. A lot of times, people would go off in just weird directions, get obsessed with trying to identify guns or something that wasn't really important to what we were doing. Similarly, the engineers commented that designers often experience technology blindness. As one of our research scientists, who's an AI research scientist, commented, it used to be that UX designers just made static marks and there was screen-to-screen flow. But with AI, the probability that end users make it through that path is lower because it's driven by a sequence of machine learning models, and the probability space is much more widely open. You need to understand the failure cases. Sorry. Understand confidence and how you deal with confidence scores and thresholds. You need to be able to understand the grain of the technology. Additionally, these design engineering boundaries, because they enable designers and engineers to work independently, they tend to commit or concretize their design even before they align the AI with the user experience. And this form of premature specification leads to frustration during coordination. As one of our engineers said, with conventional design, like I mentioned earlier, the designer just creates the specification and hands it off to the engineer. But that doesn't really work for AIX design. So one of the engineers says they would hand off that design document to the engineer and say, implement this. And of course, my reaction was, this is garbage. This does not reflect the appropriate architecture for implementing this thing. It felt particularly extraneous when it got very granular, and it was not the best medium for describing the desired behavior. Because the designers were not technical really, this is not a good reflection of how the actual software engineering is going to happen. And I was like, stop trying to do my job for me. Similarly, what happens, an alternative to this UX first approach is that AI engineers would create these AI capabilities and then go to designers and say hey, can you find a way to incorporate this within the product or the user experience? And the designer Ewan says, in the first meeting, the AI team were just saying, we just need to add this AI capability on the screen. Can you find where is the right place? Then I need to work a little backward to say that there are constraints on the wordings, and voice UI has another layer of constraints. So I need to understand how this information fits into the screen we already have. They have their own taxonomy on what kind of information they're kind of looking for, but for users, it does not evoke a response. And lastly, these boundaries restrict access to collaboration and co-design between designers and engineers. One of the designers who was trying to get into the data annotation process, but experienced challenges, told us during the interview, it seemed very odd to me that as a designer, we were not invited to the annotation session. So we had to invite ourselves just to talk to domain experts. For engineers, their approach is more like the machine is going to figure it out. We could be talking about health or elephants in a circus, and it is all the same to them. And when we asked engineers about their involvement with UX designers, they said the UX might complain after the fact that they were invited early enough. But on the flip side, if we try to involve them early, then they'll say they're busy doing X, Y, and Z. Now, because designers and engineers, like AI engineers especially, have different priorities and incentives, there is less opportunity for collaboration. So what ends up happening, because of these issues, in many of the organizations we interviewed, teams took an AI-first approach to design, in which researchers and engineers would first develop the technology, and then designers were brought in to craft the user experience around it. And as we observed in the gender shades paper, if we discover after the fact that the AI does not work for certain subgroups of people, not only are they harmed, but incorporating these fixes into AI software requires costly rework. But there is hope. We also discovered that teams that were successful in operationalizing the guidelines practiced deliberate leaky abstractions at the boundaries, which allowed them to collaborate better. In traditional software practice, leaky abstractions are considered a bad thing. But in AIX design, rather than strict abstractions and information hiding, teams shared low-level details about design and engineering with each other, and even with potential end users. As one of the data scientists told us, I prefer to learn their language at least to some degree. Obviously, I'm not going to get to know it as well as they do, but if I can learn it enough, we can reach some kind of common ground. Certainly, they need to learn my language a little bit, but I kind of feel that's on me. So to illustrate the practice of leaky abstractions to overcome knowledge blindness that I mentioned earlier, here is a quote from manager, one of the product managers we talked to. They say, as a lot of times people are just kind of down in the weeds, really deep and getting lost in the day-to-day work. UX teams can actually bring a little hope to those folks and give people a target and really paint a picture through design visualizations, whether that's making a movie or just making a series of mocks or building an experiential prototypes. So unlike in conventional software practices in which designers don't usually go to engineering teams with like, raw inputs and feedback, but in this case, this was actually desirable. Similarly, we noticed that engineering teams would create these prototypes to help designers understand like the AI's capabilities and the things it can do. One of the software engineers told us, we got something tangible enough that we could actually go talk to a designer and be like, here's what we're thinking. We started letting them play around with it and said, try it out for a week and tell us if this is better than the old way that we've done things. It also broke the problem down such that the designers understand, here's the benefits of where the machine learning can be applied. Further, these leaky abstractions promote design collaboration. That is, through like abstraction leaks, designers and engineers were able to collaborate and better align the AI and UI design. One of the user interface designers who was working on this food recommendation, an AI-based food recommendation system, told us, let's say I'm doing food recommendations and I want to tell users why something was recommended. That is explainability. I make a Wizard of Oz prototype where I first get the user's data. Then I get the model output from the data scientist and work with them to understand the model labels and explanations. The data scientist wrote down all the equations and explained it to me very clearly. They showed me how the weights were set and we discussed things that we needed to know from the user. As you can see, like, engineers are required to share these low-level details about how they have implemented the models and how the weights are set in order to surface explainable features back in a human-friendly, in the user experience design. And similarly, engineers reported finding things like storyboards very helpful in the initial brainstorming of these AI capabilities. As one of our software engineers says, I find storyboards very helpful. Storyboards are the documents that get into describing what the purpose of the behavior is, what the desired user experience is, without getting into the engineering. I think of it as sort of a comic book illustration of what the user experience should be and what the system reaction should be in different interactive situations. Here is a situation and what should happen over the course of this interaction. It's really useful to have that kind of back and forth with people who are trained to carefully think about user experience. And lastly, leaky abstractions also bring some level of transparency in evaluating the AI experiences. As one of the engineers said, there are rules and codes that we have used for making recommendations. We would list out the rules and so that the domain experts could look at it. We started giving them more accessible tools like sharing a spreadsheet where they could edit some inputs and we could import that into the system. They had the ability to flag, add notes and annotations. And in another organization where they were creating this AI-based image search algorithm, the engineer kind of describes the process of how they went about finding out what is the best way to match an input image from the user to like a set of search results. They say the process involved 20 different prototypes. I had to build for all of the different algorithms that we tested. Because AI is a black box, we need to have some transparency for the user to understand. Once you input an image, the prototype will do a search and return the results. And for each result, I showed a pre-indexed palette to compare with other algorithms. So you have that side-by-side view. Every week when we have a new algorithm, we compare it to the existing best and see which one is still the winner, and that will compete with the next algorithm. That is how we arrived at the one that shipped to production. So across all our interviews, participants reported these boundary representations that embodied abstraction leaks to support collaboration. To communicate user needs for training data, designers would create these qualitative code books or even share personas and profiles to engineers in order to think about what kind of representative data they should be collecting. To communicate user needs for AI behavior, they would share pre-labeled ground truth data, low fidelity prototypes, as well as user scenarios. And we also noticed that in some sessions, participants would share raw video footage of end users evaluating the AI system as raw feedback, as well as involved engineers in participating in these UX evaluations. Similarly, engineers communicated data characteristics for UI UX design by sharing computational notebooks with pre-formulated queries or sharing training data specifications. And to communicate model behavior for UI UX design, engineers would create like dashboards and annotate on top of wireframes what the API inputs and outputs are, as well as create these prototype demos. And finally, engineers would create these interactive prototypes where the designer could directly kind of tune the model and set different parameters and edit like assumptions and rules through a more friendly, accessible interface. So to conclude this piece of work, abstraction leaks kind of provided team an alternative to the AI-first design workflows. In the early design stage, designers and engineers would produce this fuzzy or partial design specifications. By sharing these initial design artifacts, teams could collaboratively assess, negotiate, and revise their design choices. For instance, by sharing emerging AI behavior specifications, designers can evaluate assumptions and fit for end users, update their own design representations, and provide feedback for AI design. During this stage, avoiding committing to specifications makes the design pliable and invites collaboration and inputs. As the design progresses, more and more aspects of the AI and UX components becomes concrete, and consequently, the need for leakiness at the boundary reduces. And in the final stages, teams arrive at design solutions that are aligned across AI, UI, and people. As one of our engineers kind of captured this process succinctly, they say, I think the process that works best is fairly tight review cycles with the actual evolving behavior artifacts. So building on these findings, I have conducted like subsequent work where I've developed an AI process model for collaboration and also developed tools to support this vertical prototyping between AI and UI components. In the interest of time, I'm going to briefly talk about a tool I built for prototyping AI-powered user interfaces. Now, given the probabilistic nature of AI experiences, as I mentioned in one of the participant quotes, prototyping with real data and model outputs offers designers this sort of firsthand experience of AI's capabilities and limitations as they're thinking about the user interface design. But unfortunately, most UI prototyping tools assume a closed box view of AI, making it challenging for designers to explore model behavior and access model features and outputs during the prototyping process. Designers may need to work with separate tools for model exploration and interface evaluation across diverse users and their contexts of use. And this disrupts their rapid and iterative prototyping workflow. So in Proto AI, my approach kind of combines model exploration, UI prototyping, as well as design evaluation in a single workflow that I call model-informed prototyping. I developed a tool called Proto AI that implements model-informed prototyping, and I'll quickly give you a demo of this tool. Proto AI consists of 4 main tabs, as you can see on the left. The first is a collection of machine learning models and services that the designers can incorporate in their prototyping process. The second is a data view for exploring machine learning models with diverse input data. The third is a standard user interface tab, but the designers can also directly incorporate model outputs into their design. And the last tab is to evaluate the interface design across diverse input data, and designers can flexibly work across these 4 tabs. To illustrate the core features of Proto AI, let us imagine designing a simple application that takes an input image and assigns it a label using image classification. The designer first selects the image classification model and then navigates to the data tab. Based on their user research, the designer has curated a set of images, say of different bird species. They upload this data set from a CSV file that consists of an image and ground truth labels. The designer configures these columns in a model card on the right and then runs the model for the uploaded data. For each image, the model returns 3 labels along with corresponding confidence scores. Next, the designer navigates to the user interface tab and prototypes the main logging view. After adding a header, they navigate to this Data Elements tab. Here they see the input data along with the model output, which they can directly incorporate into their interface design. After prototyping an initial layout with the image and the model generated label, the designer navigates to this Data Previews tab. Here they can see auto-generated previews of their interface design for all of the input data points and corresponding model outputs. And based on ground truth data supplied by the designer, Proto AI automatically tags erroneous classification instances. To further investigate these errors, the designer navigates to the interface tab and includes the confidence score on the interface. Now, because this is meant for the designer to investigate the errors and not part of the final design, the designer toggles the is explanation flag on the element. And in the previous tab, they see that labels with confidence value less than 60 tends to be incorrect. To mitigate these errors, the designer decides to create a new interface state for instances with low confidence state, sort of a mixed initiative dialogue. So here they're configuring this new state where they say if the classification accuracy is less than 60, then that this new low confidence, low accuracy state be shown to users. And in this new state, the designer prototypes this mixed initiative dialogue by presenting all the model labels along with the option for end users to enter their own labels. Back in the previous tab, they see this new state applied to instances with erroneous labels. Proto AI also allows designers to transform their model outputs into end-user-friendly formats for presentation. Here, the designer is transforming the confidence score into a categorical value of high or low. Lastly, Proto AI allows designers to flexibly set the data context for their interface and design across different user personas. And the widget features in Proto AI makes it easy to prototype for standard AI design patterns. In summary, in model-informed prototyping, designers can directly work with diverse end-user data, incorporate model features and outputs, supply ground truth values, and create derived data to rapidly and iteratively prototype AI-powered interfaces. Proto AI offers the flexibility for designers to specify model requirements upfront through hard-coded data or incorporate existing models and services into their prototyping process. Designers can simulate a variety of usage scenarios through the facets and interface states features in Proto AI. Such a workflow could allow designers to prototype diverse AI experiences. Recall Twitter's biased image cropping issue. Proto AI could allow designers to evaluate model performance upfront with a variety of images with different background and foreground objects and foresee the need for manual cropping features. In a different scenario, such as designing the user experience over time, such as in Netflix, the designer can start with personas with different interests and time of use. And as shown in the earlier demo, Proto AI could allow designers to prototype mixed initiative designs to account for AI's uncertainties. I'll now briefly tell you about what this all means for designing AI experiences for human learning and my future research agenda. In my own experience building AI-powered tools for human learning, a key question is what is the right balance between automation, augmentation, and the necessary manual effort on the learner? For instance, you can use AI to automate problem solving, or you can develop an intelligent tutor that guides students step by step. But the reality is students benefit from a combination of these approaches. And finding this intersection between what people need and what AI can do requires multidisciplinary expertise. I am interested in looking at ways to support early participation from learners, educators, learning scientists, and policy experts. That is, we need to identify ways to bridge knowledge and abstraction barriers across all these different stakeholders and think about boundary representations and design tools for co-creating AI experiences. One of the problems I'm interested in is in researching around AI failures and human handoffs. Now, given AI's uncertainties, we are dealing with this bad tutor or a faulty calculator problem. And I'm interested in exploring the impact on human learning from AI failures and developing mechanisms and design tools to support error recovery and handoff for human learners. And second, like self-explanation, elaboration, and inference generation sort of plays a key role in human learning. And I'm interested in studying how AI's explainability features could support or interfere with human learning, and what kind of interface interactions and presentations of explanations are appropriate in a learning or education context. That concludes my talk today. The key takeaways are that design engineering boundaries lead to knowledge blindness and premature specification. Leaky abstractions, unlike conventional software design, these abstraction leaks become necessary for collaboration with people with differing expertise. And deferred specification through vertical prototyping and constant evaluation reduces friction in the AI experience design process. Thank you for listening, and I'm happy to take questions and get your feedback.